So my name is Daniel Zentai, and I'm a cryptography researcher at xtendr, a small company in Hungary. And I will talk about a hashing protocol that multiple parties calculate together. And first, I would like to give some introduction and our motivation about this protocol. The introduction includes the difference between anonymization and pseudonymization. And I will describe actually two protocols. The first version of the protocol includes every participant to take part in the computation. And we also describe a threshold version where any certain element subset of the participant can calculate. And I will also talk a little bit about our future directions. So let's suppose we would like to store customer data in a common database from different sources in a way that the data subject in the database are not identifiable from the given information. So in order to do it, we partition the data attributes into two different sets: the identifiers and the attributes. We call the data type identifier if a data record is uniquely identifiable with it, like a passport number or ID card number, or, for example, a name and the address together. So these are the identifiers. We will anonymize these type of data, and the other set of data is the attributes, which are most common identifiers. Sorry, not identifiers. The most common data about a person, and nobody can be identified with it, like a hair color or age or something like that. Sometimes it's not that easy which is an identifier and which is an attribute, because, for example, the height of the tallest person in the world is a pretty unique identifier. So there are some cases where it's not that clear what can we choose as an identifier and what can we choose as an attribute. But this is our assumption that we can distinguish between these two types of data. And we will propose a protocol that enables a set of participants to anonymize these identifiers in a way that the rest of the data, which are not identifiers, are still accessible by the participants, and they can run some queries over these data. So, for example, a potential use case could be if different hospitals merge their data in a common database, and they want to make some statistics out of it. Like they would like, for example, run a query like how many participants with lung cancer are between the age of 40 and 60. And they want to get an answer to these kinds of questions without revealing the identity of anybody in the database. So we want to anonymize the identifiers, and we want to make accessible the rest of the data. And there is a difference between anonymization and pseudonymization. It's not a formal definition; it's a legal definition. But a data is considered anonymous if the original data can no longer be recovered under any circumstances. And if the original data can be recovered, for example, with a decryption key, then it's no longer anonymous data. This part is called pseudonymization, and from a legal perspective, it's a weaker version of privacy. So from this definition, we already can conclude then that if we want to anonymize the data, we cannot use encryption, because by definition, every encryption algorithm has a corresponding decryption algorithm. So the requirement of anonymization is not fulfilled in this case. So the first thing that that comes to our mind is probably a hash function, because a hash function doesn't have a corresponding dehashing algorithm. It's a one-way function. But if we simply hash the identifiers of the data records, then anybody who have access to the hash values can brute force it, because personal identifiers are most of the time pretty easy to brute force. For example, in Hungary, ID cards have an identifier which contains six decimal digits and two letters from the English alphabet, and that is not a very high complexity identifier. So usually these kinds of data are pretty easy to brute force, and we don't want to enable that. So the second thought we had is a kind of a keyed hash function. Like the participants have a key, and they include this key value into the hash function. And in this case, we can protect the data from outsiders, but still the participants, if they know the key, if multiple participants know the same key, then they can brute force each other's data. So one hospital can brute force the other hospital's patients. And the third thing that came to our mind was a hash function, which is once again a keyed hash function, but every participant have a different key. And if we can do this, then the participants cannot brute force each other's data, because they don't know, even if the ID is a low complexity string, they still don't know each other's keys. So the problem with the third approach is if we reorder the keys, then it changes the hash values. At least this is how most of the hash functions works. Not all of them, but most of them works this way. And this is a problem because if another participant wants to anonymize the same plain text, we want the result to be the same, because otherwise the statistics will be distorted. So we want to detect the data records that are in the database of multiple participants. And we came up with the following idea. Oh, sorry, first of all, the requirements as a summary. So the transformation that we use should be a one-way function. The results should be hard to brute force, and a certain subset of the participants performs the computation together, and the output should be the same regardless of the order of the participants in the computation. So these are our requirements right now. And this is a building block of our protocol. This is not a hash function we developed, but this is a well-known hash function, but not a widely used hash function, because it is pretty slow compared to the most popular hash functions. So basically, it hashes two values together, x and y, and x and y here are elements of a cyclic group with cardinality p, which is a big prime number. And if we want to hash x and y, then the hash value will be a to the x times b to the y modulo p. And here a and b are two primitive elements of the cyclic group. And it has been proven decades ago that this hash function is collision resistant if the discrete logarithm problem is hard. So we will use this as a building block of our protocol. And the protocol works like this. So we will assume that the participant who wants to anonymize the data is P1. And P1 wants to anonymize the data record M. And P1 first sends an upload request to a trusted server, S, and then S generates n random numbers and sends them to the participants. So if a participant, if the first participant receives the random number R1, he calculates H1, which is the hash value of X1 plus M and Y1 together. Oh, sorry, I didn't mention X1 and Y1 is a private secret value from the participant P1, and every participants have two secret values. Participant I have a secret value Xi and Yi. These are our assumption. So here P1 sends this hash value to the server together with an encrypted version of R1, encrypted with the public key of the server. And all other participants, they don't have this value M. They just hash their X1 and hash their X and Y values together and sends this H sub I, which equals to H of Xi, Yi, and sends it to the server together with the random value they received. And if the server receives a hash value and an encrypted random number from the participants, then the server checks the random values together, R1, R2, Rn, and if they matches the random numbers he sent out in the first step, then the server stores the multiplication of these hash values. So here the purpose of these values is not authentication. This is just enables the server to check that everybody indeed took part in the computation. This is the only purpose of these random numbers. And also, since the protocol is not designed to develop a secure channel, it's only designed to store some data, calculate and store some hash values. Then we will assume throughout the whole protocol then that then the server and the participants can communicate over a secure channel, like SSH or TLS or something like that. So this is a pretty strong assumption, but again, the protocol is not designed to develop a secure channel. Okay, so if the server have every hash value and it multiplies together all of them, then what it gets at the end is this hash function here, but in the exponent we have the ID plus the sum of the x values times b to the power of sum of the y values. So whatever was the order of the participants in the computation, the final hash value will be the same, because if we multiply these values together, we always get the sum in the exponent. So this is just a quick comparison between the running time of two versions of the protocol, because we can do the same protocol in any algebraic structure where the discrete logarithm problem is hard, and if we do it with elliptic curves, we get a huge improvement in running times. For example, if we have 15,000 participants, then the running time over z sub p is a few thousands of seconds. And if we do it with elliptic curves, it's only 120. So it's almost a 20-fold speed up if we do it with elliptic curves. Now we also have a threshold protocol, and we will use Shamir's secret sharing scheme as a building block of this protocol. So in the first version I described right now, there all of the participants had to participate in the computation. And here we will describe a relaxation where not every participant, but if we have n participants, then every k-element subset of them can calculate the same value. And the output of the protocol should be the same whichever k-element subset we choose. So We already saw Shamir's secret sharing in another presentation today, but just a quick reminder about it. So let's suppose we have a finite field, and S0 is an element from the finite field. This is a secret we want to share amongst the participants, and we choose k-1 random elements from this field, and we define a polynomial f of x like S0 plus the sum of ai times x to the I. And each participant, pi, is given a point of this polynomial, x sub I, f of x sub I. So everybody just get one single point of the polynomial. And with Lagrange interpolation, any k-element subset of the participants can recover the polynomial, and therefore they can recover the constant value of the polynomial, which is the secret itself, like this. So first, they have to calculate these L values. L sub I equals the product of xj over xj minus xi for all j value which not equals to I, and then the constant value of the polynomial is the sum of f of xi times li. So this is Shamir's secret sharing, and basically what we want to do is to build this polynomial in the exponent of the hash function. So first of all, S generates two secrets, S0 and T0, and distributes them using this secret sharing scheme to the members in P. And then S uses two different polynomials, f and g, and also the participants generates, in this case, only one random value, not two. So here, if any of the participants knows the polynomial, then the participant also know the value, the constant term of the polynomial, and then he can start to brute force the hash value. So the participants cannot know the polynomial, and the server don't know the x values. So we have to, this is the first tricky part, because we have to calculate the value of the polynomial on these x points. But the server knows the polynomial and not the x values, and the participants knows the x values but not the polynomial. So we have to use a fully homomorphic, not. Oh yeah, we have to use a fully homomorphic encryption scheme in step 2. So first of all, every participant encrypts this x value with his own public key and sends it to the server. And the server evaluates the polynomial f and g over this encrypted value. And since in this case this is a fully homomorphic encryption, then it will be the same as if the server evaluates the polynomial over the x value and then encrypt it and sends it back to the participant. And the participants can decrypt it, and they will know the value of the polynomial over their own x value, but nothing else. Then every pair of participants shares with S a quotient of neighboring x values, xi plus 1 over xi, with a multiplication protocol I will describe a little bit later. And if the server requests an anonymization, server receives an anonymization request from P1, then the server randomly chooses a k-element subset of the participants. And let's assume this k-element subset is P1 through Pk. And S generates once again k pieces of random value and sends this random value to the participants in this subset over a secure channel. And then every participant can now calculate these L sub I values, which is, as I said earlier, the product of xj over xj minus xi, and the server calculates these values and sends L sub I to P sub I. And upon receiving R1 and L1 from S, P1 calculates the hash value, which is in this case the hash of m plus f of x1 times L1 and g of x1 times L1. So at this point, P1 knows the message and he wants to anonymize it, and he also knows the f of x1 and the g of x1 because he received it from the server, and he also knows L1 because he also received it from the server. And he sends this value back to the server together with the encrypted R1. And for all participants, if they receive this random value R sub I, then they calculate the hash value of f of xi times li and g of xi times li, and sends it to the server together with the encrypted R value. And upon receiving these values from all of the participants, I mean all of the k participants in the subset that S chooses, then once again S have to multiply these values together, and if he multiplies these values together, we will get a to the m plus s1 times b to the t, sorry, not s1, s0 times b to the t0. So this is the value whichever k element subset we choose at the beginning. So another tricky part I have to mention is the multiplication. So if we go back one step earlier, here the participant P sub I has to know the quotient one more step earlier. So in step 3, in the participants P sub I and P sub I plus 1 have to know the quotient of x sub I plus 1 over x sub I. But the problem with this one is P sub I cannot know the secret value of x sub I plus 1, and P sub I plus 1 cannot know the secret value x sub I. So we need a protocol, a subroutine to calculate these values. And the protocol is pretty simple. First of all, let's assume that that two participants, P1 and P2, wants to calculate a product of two of their values, x and y, without knowing each other's secrets. So P1 only knows x and P2 only knows y. And first of all, P1 generates a random number R1 and sends R1 to x, R1 times x to P2. And P2 generates another random number R2 and calculates R1 times R2 times x times y. So this is the product of the two secrets values multiplied by a product of two random values generated by the participants. And P2 sends it to the server. And the server also generates a random number and multiplies this result with his own random number and sends it back to P1. And then P1 multiplies it by the inverse of his own random number and sends it to P2, who then multiplies it with the inverse of his own random number and sends it to the server. And then the server will multiply it with an inverse of his own random number. And the server then can learn the product of x and y without knowing x and y separately. And the participants won't know each other's secret value either. Okay, so this is the threshold protocol, and about a few words about our future directions. So first of all, we have some ideas about those, but they are not finished articles. So it would be nice to generalize this idea such that it can work with any hash functions, some well-known and more efficient hash functions, and also the discrete logarithm based version is not post-quantum, because the discrete logarithm problem is crackable with a quantum computer. So that's another direction we want to move, and also the decentralization of these protocols would be a pretty reasonable next step to eliminate a trusted server. And that's all I wanted to tell you. So thank you very much for your attention, and if you have any